In this lesson, we want to review rationalizing the denominator. So in order to present a simplified radical as an answer, you have four criteria that you need to meet. So first and foremost, we say that the radicand, that's the number under the radical symbol, has no factor raised to a power greater than or equal to the index. Now, what does this mean in layman's terms? We already talked about this a few lessons ago. Essentially, if you had something like the square root of 20, the index here is a 2 on a square root, so you don't want any factors of this radicand, this number 20, to be a perfect square. So with 20, we know this would factor into 4 times 5, and 4 is a perfect square. So we could write this as the square root of 4 times the square root of 5. This guy would represent the rational number 2. So we would just write this as 2 times the square root of 5, and that would be considered simplified, okay? If you had a cube root, then you don't want any factor of the radicand to be a perfect cube. If you had a fourth root, you don't want any factor of the radicand to be a perfect fourth, so on and so forth. All right, the next item on the list, the radicand has no fractions. We learned about the quotient rule for radicals. That's how we can deal with that. If you had something like, let's say, the square root of 12 over 25, we could break this up into the square root of 12 over the square root of 25. We know the square root of 25 is 5, so let's just write that down there in the denominator. For the square root of 12, we can simplify because it's 4 times 3, right? That's 12. So we have the square root of 4 times the square root of 3. So this guy right here, again, square root of 4 is just 2, so I can end up writing this as 2 times square root of 3 over 5, okay? Then this guy right here is the subject of today's lesson. We have no denominator contains a radical. So if I had something like, let's say, 4 over the square root of 2, we don't want a radical in the denominator. That's considered not simplified. So the process we use to clear a denominator of any radicals is known as rationalizing the denominator. Okay, and we'll talk about that just in a second. Now, lastly, we see that exponents in the radicand and the index of the radical have no common factor. So what this means is if you had something like, let's say, 5 to the 6th power, and let's say you had the 9th root of that. Well, between the 9 and the 6 there, you have a common factor of 3. So you can quickly say, okay, if I divide 9 by 3, I get 3. And if I divide 6 by 3, I get 2. So this would be the cube root of 5 squared, or basically the cube root of 25. Now, if that doesn't make sense for you doing it that way, you can always convert this to exponential form. You can say I have 5 to the 6th power raised to the 1/9 power. And of course, you can use your power to power rule. So this is 5 raised to the power of 6 times 1/9, which is 6/9. And from there, you can just simplify the fraction. 6 and 9, again, each have a common factor of 3. Divide 6 by 3, you get 2. Divide 9 by 3, you get 3. So this ends up being 5 raised to the 2/3 power, which again is just the cube root of 5 squared, which is the cube root of 25, okay? It's just simpler to divide here than to go through all this with the exponential form. But if it's something you struggle with, something you can't mentally comprehend yet, then go ahead and take the time, convert it to exponential form, and then you'll be good to go. Let's talk a little bit about rationalizing the denominator now. It's a pretty easy concept overall. So if I had something like 5 over the square root of 2, realize that you have a radical in the denominator. And again, if you want to present a simplified radical, this is not allowed. So right now, this square root of 2 is an irrational number. Okay, it's an irrational number. So in decimal form, it does not terminate, it does not repeat. So to simplify this, all I really need to do is multiply the numerator and denominator by the square root of 2. And let's think about why that works for a second. The first thing is the square root of 2 over the square root of 2 represents the number 1, right? It's just a complicated form of 1. I can always multiply by 1, and I leave my number unchanged. So I'm not doing anything illegal. In the numerator, 5 times square root of 2 is just 5 times square root of 2. Nothing fancy there. In the denominator, what's going to happen is square root of 2 times square root of 2 is the square root of 2 squared, or the square root of 2 times 2, which is just going to be 2, right? It's the square root of 4, which is 2. So this is going to be equal to 5 times square root of 2 over 2. So now this 2 is a rational number. So I've changed my denominator from an irrational number to a rational number, henceforth the term rationalizing the denominator. So basically to do this, especially if you're just working with a square root, just make sure your square root is simplified first. And then once that's done, just multiply the numerator and denominator by that square root. So let's look at another example. So if I had something like 6 over the square root of 3x. This guy right here is already simplified, so I'm just going to multiply this by the square root of 3x over the square root of 3x. And what would I get? 6 times the square root of 3x is just 6 times the square root of 3x. Down here, the square root of 3x times the square root of 3x is just 3x. Now I'm not done because I can simplify further. Between the numerator and denominator, I have a common factor of 3. So this divided by this would give me what? That's gone. This would be a 2. So I end up with 2 times the square root of 3x over x. And that's my final answer. I can't do anything else. But again, notice how I don't have an irrational number in the denominator. I just have an x. All right, for the next one, we're going to look at one with a higher level root. So we have 7 over the cube root of 2. And essentially what I want to end up with is something in the denominator that's the cube root of something that's a perfect cube. So if I think about 2 times 2 would be 4. 4 times 2 would be 8. So I want to end up with the cube root of 8 because 8's a perfect cube. So I'm going to multiply this by the cube root of 4 because 2 times 4 would give me 8. And I got to do the same thing to the numerator to make it legal. So I would have 7 times the cube root of 4 over. Again, in the denominator, the cube root of 2 times the cube root of 4 would be the cube root of 8, which is just 2. Right? So I'd have 7 times the cube root of 4 over 2. All right, for the next one, we'll look at 15xy over the cube root of 25x squared y. So if I think about 25, it's 5 squared. I know x squared is just x squared, and I know y is y to the first power. I need a perfect cube under here. So what I'm going to need is 5 cubed, I'm going to need x cubed, and I'm going to need y cubed. So what am I missing to get to 5 cubed? I just need a 5. So I'm going to have the cube root of 5. And then what am I missing to get to x cubed? I need an x. What am I missing to get to y cubed? I need a y squared. Okay? So everything under there would basically be a perfect cube after it's multiplied. So if I go through here, and I'll deal with the numerator in a second. If I go through here and multiply, 25 times 5 is 125. X squared times x is x cubed, and y times y squared is y cubed. So if I take the cube root of this, again, this is a perfect cube, I'm going to end up with 5xy as my denominator. Okay? So once I've figured that out, the numerator part is pretty easy. I'm going to have 15xy multiplied by the cube root of 5xy squared. So I'm just going to write this here. We have 15xy times the cube root of 5xy squared. And again, one more time down here. So 15xy times the cube root of 5xy squared. And we can do some simplifying here. We see between numerator and denominator, we have a common factor of 5, so this becomes 3. We have a common factor of x, so that's gone. And then we have a common factor of y. So this guy will cancel with this guy. And I'm basically just left with a 3 multiplied by the cube root of 5xy squared. Let me make that a little better. All right, let's take a look at another one. So we have 2x minus 5y over the fourth root of 125xy cubed z squared. Again, if I have a fourth root here, I'm looking to make this into a perfect fourth down here. So for 125, I know that's 5 cubed. For x, I know that's x to the first power. We have y cubed, and we have z squared. So what do I need to do to make this into a perfect fourth? 5 cubed, I'm missing a 5. X to the first power, I'm missing an x cubed. Y cubed, I'm missing a y. And z squared, I'm missing a z squared. So I need to multiply the numerator and denominator by the fourth root of 5x cubed yz squared. Okay, let me erase this. So this is equal to, I've got to be careful here because when I multiply this by this, This is two terms here, okay? So I've got to make sure that each term is multiplied by this. So I'm going to use some parentheses. I'm going to put my fourth root of 5x cubed yz squared out in front. And inside of parentheses, I'll have 2x minus 5y. Again, with two terms there, this has to be multiplied by each term. Then this is over. If I multiply these guys, I'll have the fourth root of 125 times 5 is 625. X times x cubed is x to the fourth power. Y cubed times y is going to be y to the fourth power. And z squared times z squared is z to the fourth power. So notice how we have a perfect fourth down here. So let's go through and keep simplifying. And I'll scroll down and get a little room going. So I'll have my fourth root of 5x cubed yz squared multiplied by the quantity 2x minus 5y. Then this is over. This guy right here, the fourth root of 625 is 5. Then the fourth root of x to the fourth power is x. The fourth root of y to the fourth power is y. And the fourth root of z to the fourth power is z. Now I can go through and I can distribute this to each term if you want, but it's not really necessary because this is as simple as we can really make it. But for the sake of completeness, we will clear these parentheses. So we'll say we have 2x times the fourth root of 5x cubed yz squared. Then minus, you're going to have 5y times the fourth root of 5x cubed yz squared. Then this is all going to be over. You're going to have that 5xyz. All right, let's talk a little bit about rationalizing a binomial denominator. So for this guy right here, it's a pretty easy concept. You're going to use your formula for multiplying conjugates to clear a binomial denominator that has a radical in it. So what do I mean by that? I want you to recall that if you have x plus y multiplied by x minus y, remember these guys are called conjugates. It's the same first terms, it's the same last terms, you have different signs, so a plus and a minus. When you multiply these two together, the middle two terms drop out. So you end up with just the first term squared minus the last term squared. So what's going to happen is I'm going to multiply this by, we'll have the square root of x minus 3 over the square root of x minus 3. Okay? So what I did was, in my denominator, I now have the product of conjugates. It's the same two terms, so square root of x and square root of x, 3 and 3, but different signs. So what's going to happen is the middle two terms are going to drop out. They'll cancel, and you'll be left with the first term squared, square root of x squared is x, minus the last term squared, 3 squared is 9. Okay? So if you want to go through that the long way, square root of x times square root of x is x. The outer would be minus 3 times square root of x. The inner would be plus 3 times square root of x. So you can see those would cancel. And the last would be minus 9. Okay, so this is gone, and you're just left with x minus 9, right, which is exactly what you have there. Then in the numerator, we basically have 1 times this quantity, which is just that quantity. So you get the square root of x minus 3 up there. Okay, nothing you can really do here to simplify further. So we just have the square root of x minus 3 over x minus 9. All right, let's take a look at another one. So we have the square root of x over 3 minus the square root of x. Again, I'm just going to multiply the numerator and denominator by the conjugate of the denominator. So I would have 3 plus the square root of x over 3 plus the square root of x. Again, it's the same two terms in the same order, just change the signs. Okay, that's all you've got to do. So in the denominator, I would just square the first guy. 3 squared is 9. Then minus square the last guy. Square root of x squared is just x. And then in the numerator, we would basically have 3 times square root of x. And then plus square root of x times square root of x would be x. Nothing else I can really do to simplify here. So 3 times square root of x plus x over 9 minus x is your answer. All right, for the last one, we'll look at one that's a little bit challenging. So we have 3x over, we have 2 plus the square root of x plus y. So the idea is to treat this as the first guy and this as the second guy. So if I want to multiply by conjugates here, I'm just going to say this is 2 minus the square root of x plus y. And then down here, I'm going to put 2 minus the square root of x plus y. Okay? So when you go through and multiply, it's the same principle. You'd square the first guy, which is 2. So that's 2 squared, which is 4. And then minus, you'd square this guy right here. So if I squared the square root of x plus y, I would just get x plus y. But you got to be careful because you got to subtract the whole thing away. Okay? So this would be minus x and then minus y. In the numerator, you would have 3x times 2, which is 6x. And then minus, you would have 3x times the square root of x plus y. Now, nothing you can do to simplify this further. You just get 6x minus 3x times the square root of x plus y over 4 minus x minus y.